Alright, here we go. Run 22. The heights of women are approximately normally distributed with a mean of 62 and a standard deviation of 3.5. I suppose I should put inches. Usually you have units. A, find the probability a woman is taller than, sort of a randomly chosen woman I suppose, is taller than 60 inches. So we do that since it's a normal distribution by computing a z-value. So z is x minus mu over sigma, that's z. So x is the value, mu is the mean, sigma is the standard deviation. So we're reading about 60 minus 62 over 3.5. It gives you a number. The number is the number of standard deviations away from 0 that z is. So it's below the mean, so you get a negative answer. So it's minus 0.57. So about half a standard deviation below the mean. We'll go to the tables. The tables will give the proportion less than that or the probability of being less than that. It's 0.2843. We want taller than 60, so it's the other side of the curve. So what are we thinking? Over here, I suppose. Here's our distribution. 62 is here. 60 might be about there. Taller than 60 would be this side. The tables give this side to be 2843. So this upper side is 0.7157, 1 minus 2843. But we can ask the same question for a sample of 9 women. What is the mu and sigma? Oh, it's not the same question. It says just tell me mu and sigma. That should be easy enough. So mu, if you take the mean of some observations, the average, if you take the mean of the average of 9 observations, is the same as the mean of the population. So the mean doesn't change, stays 62. However, averaging decreases the standard deviation. It divides it by the square root of n. It used to be 3.5. Now it's 3.5 over square root of n. So that's sigma over root n in our thinking. So root 9 is about 3, so the standard deviation is really about 1. So instead of dividing this minus 2 by 3.5 and getting 0.57 negative, we're going to take the minus 2 and divide it by 3.5 over 3, which is a little bit bigger than 1, so we'll get something slightly less in size than 2 minus 1.71. Now you think about where that sits in the new distribution. We were only half a standard deviation below before, so we would be about here for a single value, but now it's 1.71, so that's 1.71, so now we're down here. And we still want the chance of being above. If we look up minus 1.71 on the tables, I get 0.436. So that looks a tiny bit too big. It's only about 4% of the total area. And this side then, 1 minus that, 0.9564, will give the answer to the chance for x bar being bigger than 60. So what happens is, since the mean is 62, more and more values will be closer and closer to 62 as you sample more and more values and take the mean. So the chance of being bigger than 60 becomes greater and greater because the values cluster around 62, which is bigger than 60. We're over here on 24. Hypothetically, suppose I'm late for work 20% of the time. That'd be quite often. That could happen. Suppose I have to leave early from work 10% of the time. Seems like you're not working too much. And suppose the chance you do both is only 5% of the time. If the first two are independent, is this number larger or smaller than what you'd expect to see? Let's see. So if they were independent, the way you compute probabilities for independence is you multiply the two probabilities together to get the probability of both. So both should be 0.2 times 0.1 or 0.02 if they were independent. So the observed probability is a little higher than if the events were independent. So that says, if you're late for work, your chance of leaving early is probably a little bit bigger than 0.1. Is that right? It's a little higher. Well, it should be 0.2, and it's 0.05. That makes sense. So the two go together a little more frequently than you would think than if they were independent. And that probably is the way life is. If you're late for work, you might have to leave early for the same reason. Maybe you don't feel good. Maybe there's stuff you have to take care of at home. That makes sense. 25 25 is talking about a complicated situation where E is something about traffic lights and F is, let's see, there are 2 traffic lights on a route used by a certain individual to go from home to work. Let E denote the event the individual must stop at the first light, and define the event F in a similar manner for the second light. So E and F represent stopping at lights, 2 different lights. And so the P of E is the probability you stop at the first light is 0.3. And P of F is the probability you have to stop at the second light is 0.5. And suppose the chance you stop at both is 0.15. So it says make a Venn diagram. Oh, I can do this. So with these Venn diagrams, if you have E and F given to you, you just fill out the center portion, because that's both things happening at the same time with that number. It could be a probability, it could be a percent. And then if you have these other ones separately, like probability E is 0.3, these 2 numbers together have to add to be 0.3. We already had 0.15, so it has to be 0.15. And these 2 together, since they're all of F, have to add up to be 0.5, so 0.15 plus 0.35 becomes 0.5. And just for grins, the total of all the probabilities should be 1. So here I've got 3, so I got 0.65 for the total, and 0.65 plus 0.35 is equal to 1. So the outside here, that's everything else, has to be 0.35. So that's a nice Venn diagram. It says, are the events E and F independent? If they are, or they will be if, the probability of E and F equals the probability of E times the probability of F. So we just have to check that product is true. If it's true, they're independent. If it's not true, they're not. So we take 0.3 times 0.5, we get 0.15, and we jump up and down and say, look, it looks like E and F are independent. If this number times this number didn't match that one, they would not be independent. And that's all you need to check. It's a very peculiar thing, that have things not really depend on each other whether they happen or not. It's just a multiplication property of numbers. And you don't have to know the situation to tell if something's independent. All you have to do is look at the 3 probabilities. Probability of one at a time, and the probability they both happen. And if these 2 multiply to be that, then seeing one doesn't change your perception of how likely the other one is to happen. That's just how it works out. So we've got a few more problems under our belt, and there's quite a few left.